Even with perfect upper level support, storms still need one final ingredient: a focused forcing mechanism, like a boundary. Cold fronts, warm fronts, dry lines, and outflow boundaries often determine exactly where storms form and whether they produce tornadoes. In this episode, we're bringing everything together and explaining how surface analysis and soundings complete the storm chasing forecast process. I'm Gabriel Harbor, and you are listening to the Storm Chaser Coaching Podcast. Before we dive into the questions with Coach Trey Greenwood, there's a link in the description where you can get the cheat sheet for this episode. Cheat sheets contain all of the notes we use to build out each podcast episode, and if you click that link one time, you'll unlock access to the cheat sheets for every single episode we ever have or ever will record. Trey, first question: how do forecasters identify surface lows on a weather map?
So this involves doing a robust surface analysis. So that is filling in your isobars or lines of equal pressure every couple of millibars or so on a surface map. That is the standard for analyzing surface observations. Not every chase you're going to have the time to do that in the morning. So what you can look for is generally, of course, lower pressures near the center of that low pressure. But also, if you see winds that are circulating in a counterclockwise fashion around a point, that is usually a sign that you have a rotation, cyclonic or counterclockwise fashion, which often indicates a surface low.
What clues help locate cold fronts, warm fronts, and dry lines?
So when you're identifying boundaries on a surface map, you want to not just focus on one particular aspect, but you want to see a confluence of factors come together in that location where the boundary might be to increase your confidence in placing that boundary. So the first thing you want to look for is wind shifts. Is the wind to the south of the boundary, the potential boundary more out of the south, whereas to the north it might be out of the east across a broad area? That is a sign that you might have a boundary in place. You can also look for temperature gradients and moisture gradients. So, do you have, say, mid 70s temperatures on one side of the boundary and maybe 60s, low 60s temperatures on the other side? That could be a sign that you have a boundary. Also, moisture can be a boundary, an indicator of a boundary. So you might have higher dew points on one side than the other. And of course, this comes into play with a dry line. You want to see those real high dew points on the moist side of the dry line and much drier dew points, much drier air on the west side of the dry line. If you do a surface analysis as well, a full surface analysis where you're marking in your pressure contours, your isobars, you'll often see a pressure tongue associated with the boundary location as well. So the pressure lines might kink over a certain area, and that could be a signal that you have a boundary in place. Again, you don't want to focus on just one of these. Just because you have a temperature gradient across a certain area does not mean you have a boundary. You want to see also in that same area perhaps a moisture gradient, a wind shift, and if you do a surface analysis, a pressure tongue. If most or all of those boxes are checked, then you likely have a boundary in place and you have increased confidence that boundary is placed correctly.
Now, if you're thinking to yourself, this is all a lot to take in, it certainly is, but thankfully you have an additional resource to this podcast episode, which is you can join our Discord community, and there are members and coaches who are always willing to help. If you are working on surface analysis and you have some questions, what does this mean? What does that mean? People are always willing to chime in, and make sure you check your DMs after you join as well. We have an automated message that we send out, which gives you information about all the cool stuff that you have access to in our Discord community. Next question, Trey. Why are boundaries so important for storm initiation and particularly tornado potential?
Along boundaries, you typically have stronger surface convergence. So your winds are coming together a little bit better along boundaries than they are otherwise. And boundaries can have vertical circulations as well, aiding in that uplift along it that is needed to initiate storms. So that's why boundaries can be a focus for storm initiation in an environment that otherwise might have minimal coverage or you're not sure where storms might fire. Boundaries are often a starting place where you want to look for storm initiation. If a storm can actually move along and latch onto a boundary, particularly an outflow boundary or even a warm front, then they can produce tornadoes, perhaps significant tornadoes, because there is usually stronger low-level shear and vorticity along these boundaries. That spin in the low levels is maximized right along the boundary zone. That is going to be ingested by supercells or used by supercells to perhaps produce tornadoes if storms can latch onto the boundary. Usually you want your storm to be moving in a motion that's parallel to the boundary. If that storm crosses the boundary, usually that's going to mean a transition to more of an elevated nature and decrease the tornado risk overall. But if storms can actually track along the boundary zone, that is a favorable situation for producing tornadoes, perhaps strong tornadoes.
Now, what do Skew-T soundings tell us about instability and capping?
Skew-Ts are one of the most important things you can use in a forecast because it tells you the entire thermodynamic profile in the atmosphere. Basically, how unstable is it? Where is it unstable in the atmosphere, etc. So if you have that typical sounding where you have your red temperature profile, your green dew point profile, and then that dashed line off to the right usually, which is your parcel trace, when that parcel trace is to the right of the red temperature profile, so that any parcel that goes up in that given environment would be warmer than the environment itself, you have instability. If your parcel trace is to the right of that temperature profile all the way through the atmosphere, you have an unstable profile throughout the entire atmosphere, which of course is favorable for storms. Now, the thickness of that space between the parcel trace and the red temperature profile is important because if you have a skinnier instability profile, that leads to perhaps less robust updrafts than a more thick cape profile or instability profile. Now, if the environment is warmer than the actual parcel, then you have capping in the environment. So when that parcel trace is to the left of the temperature profile, that indicates stability and perhaps capping. So you'll often see a little bit of a warm nose in the low levels of a sounding, oftentimes in the morning of a severe weather event, where the red temperature profile will jut off to the right a little bit and then back to the left. That is a warm nose that is often indicative of a capping inversion. And of course, if you have that in place, that can allow for instability to build and build through the day until that cap erodes and you can get explosive storm development. And it also keeps the warm sector, the area where storms are expected to take place, free and clear of storms early on in the day, which can also lead to that favorable environment later on for the most robust storms in the afternoon or evening.
Now we move on finally to the close cousin. I don't know if that's the correct familial relation there, but definitely something that is in the same vein as the Skew-T sounding, which is the hodograph. What does that reveal about tornado possibilities?
So the hodograph is the plot of how the winds are changing as you go up in the atmosphere. So it's basically a plot of how wind shear is constructed through the atmosphere. So you're basically plotting all your wind barbs as you go up in the atmosphere and connecting the dots, the ends of those vectors, and that's how you get the hodograph. Now, this is not a hard and fast rule. We've seen plenty of exception to it, but typically, if you have a more sickle-shaped or meat hook-shaped hodograph in the low levels with a longer portion in the mid and upper levels, that usually indicates an environment favorable for supercells and tornadic supercells when that low-level curvature is greater. Not always the case. Obviously, it depends on things like storm mode and whatnot, and instability and other stuff. And we can have tornadoes and setups that don't have that strong sickle shape in the low levels. There are other factors at play, like storms latching onto a boundary, ingesting that spin or vorticity at the surface. That can help overcome some of that weaker low level shear or curvature in the hodograph. But typically, in a very general sense, when you have stronger, more noticeable sickle shape or meat hook shape in the low levels of the hodograph, that tends to be an environment that has stronger low level shear, which is more favorable for significant tornadoes.
Remember to check out those links in the description below, and then watch another video.